Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are now starting our third lecture for the fifth week of wireless and mobile communications. In our previous lectures in this week, we discussed free space propagation modeling, and while doing so we calculated the free space path loss, and I explained that the free space propagation modeling and free space path loss model is mostly valid in the scenarios where we do not have any obstacles between transmitter and receiver. So this model can only be used where there is direct line of sight between transmitter and receiver. But in most mobile radio channels, the direct path between base station and mobile station is very rare. It's really very hard to find this direct path. Therefore, free space propagation model is inaccurate for most of the cases. For practical cases, the free space model generally predicts path loss which is much smaller than the actual loss that encounter during propagation. So in order to correct, we need some other models. For this case, typically another model is used which is named as ground deflection model or two-ray model. A two-ray ground deflection model is a useful propagation model which is usable in variety of different environments, and it gives reasonably good results in predicting the large scale path loss model over a distance of several kilometers, provided that the antenna height is reasonably high, especially the transmitter antenna height is reasonably high. In that case, this two-ray ground deflection model gives reasonably good result. The good thing is that this two-ray ground deflection model is very simple and is based on a simple geometrical optical concepts. So we can treat the electromagnetic wave as rays, and by analyzing those rays we can calculate the path loss related to that propagation. This model is named as two-ray propagation model because it's based on the analysis of two rays. In this model we choose two different rays, one ray which goes directly from transmitter and receiver, so there is a direct path between transmitter and receiver, and we take another ray which reaches the receiver by reflecting from the ground. So there is a ground reflected propagation path between transmitter and receiver. So overall effect is calculated on the basis of effect of these two different rays. This is a graphical illustration of this two-ray ground deflection model. You can see we have a transmitter. Typically we know that in mobile environment the base station antennas, they are placed at relatively large tower, so transmitter height is relatively high and receiver height is same as kind of human height. So receiver antenna is at relatively low height. So we assume that the waves which are transmitted from the transmitter, they can be treated as two rays. First ray which goes directly from this transmitter to receiver, which is represented here by ELOS. So ELOS represents the electric field component which goes directly from transmitter to the receiver. Then there is another path where another ray which is represented here as EI, it goes towards ground and gets reflected back from the ground. So there is a specific point which gets the ray gets reflected back and reaches the receiver at that receiver at the height of HR. So this ground deflected ray which is written as EG is second component. So the overall effect of the total field is actually sum of these two components, the LOS means line of sight ray or direct path ray, and EG represents the electric field which is coming from the ground. The separation between transmitter and receiver is represented as D. So this is the graphical illustration of two-ray ground reflection model. The objective is same as we discussed related to the path loss modeling, that we intend to calculate what is the received power at the receiver when we know the transmitted power. So here is the summary of what we represented in this model. So the height of transmitter is taken as HT and height of receiver is taken as HR, and typically this HT is greater than HR, which is the practical case for most of the scenarios. The transmitter and receiver separation is represented by D. Second thing, because this is ground, ideally the ground is spherical in nature, but typically the propagation distances, which are around a few kilometers, they are very small as compared to the radius of the ground. If you think of ground as a large object over which we are having this small TR separation, in that case it is a convenient choice to take ground as a flat surface. So for this model, typically we assume the ground as flat surface, and practically this assumption does not make any difference because the propagation distance is very small as compared to the radius of the ground, and it does not make any difference by taking earth as a flat object. So the total received field E total is then result of two components. First one is the line of sight component, LOS component, which goes directly from the transmitter to receiver, and the second is the ground reflected component, which is represented by G here, which represents the part of the wave which reaches the receiver after getting reflected back from the ground. Let us assume that E naught is a free space E field. Of course the unit would be volt per meter, and the reference distance D naught from the transmitter is D naught. So as we discussed, it's a common choice in mobile systems to take a reference distance. So we have chosen reference distance as D naught, and the E field which is available at that reference distance is given as E naught. So when the wave propagates from transmitter to receiver, so let's say if we have D naught here, so if the wave goes from this point to the receiver, so there will be change in the phase as well as the magnitude. Both magnitude of the wave would get reduced, and also there will be a phase difference. So what should be the field at a distance D? So at a distance D, you can see this E naught is actually the field strength at D naught, and because at a distance D the field strength will get reduced, so we typically write it as D naught by D, where D is greater than D naught. So the field magnitude, so this component is actually representing the magnitude of the field. So this magnitude or amplitude of the field is actually smaller than what you have at the reference distance D naught. Secondly, because it's electromagnetic wave, so we can treat it as cosine cosine wave with the angular frequency of omega c, and the difference which is obtained in the time delay, this d upon c, is actually the time that the wave takes from traveling from this point to the receiver point. So this d upon c is the delay time. So overall the E field can be represented by this expression, that E as a function of distance and time is given by this value. So this first part, E d naught by d, is actually the magnitude of E field at the distance d from the transmitter. But if you observe that, this is the general relationship, but you observe that there are two different rays we are talking about. First one is the ray which is going directly. So let us assume that this ray travels the distance of d prime. So in that case, this LOS wave that has traveled the distance of d prime, it should have the form that the overall wave which is received at the receiver will be E naught d naught upon distance d prime cosine omega c t minus d prime by c. Similarly, the other ray which is actually taking this path, first goes to ground and then return back. So this entire path, this entire distance has to be traveled by other ray. So this entire distance would be little bit different than d prime. So let's say we write it as d double prime. So the mathematical form of the ground reflected wave would be given in a way that the magnitude is E naught d naught upon d double prime and cos omega c t minus d double prime by c. So this is in accordance with the same equation. One important thing which you should note, that we have added a component here, gamma. This gamma is due to the ground reflection. So this gamma is actually the reflection component. The ground, this point is you have a reflection component, reflection constant of gamma here. So this gamma appears because of the reflection that you get from the ground. So this reflected wave Eg is actually gamma times Ei, which is the incident wave. In most cases, the ground is actually treated as a perfect ground deflection. That means there is no loss related to the ground, and when the wave gets reflected from the ground, it experiences a phase change of 180 degree. So this gamma can be taken as -1. So coming back to this model, you can see that the total electric field is actually now having two different components. First component is the line of sight component, and second is ground deflection component. So the total field would be sum of these two, LOS and EG, and as we are interested in calculating the magnitude of the field, the magnitude of field will be equal to magnitude of sum of these two fields. One important thing is that these two are actually vector field. Electric field is basically a vector field. So when we would add these two, so we would have to go for a vector addition. So this is the basic introduction related to the ground deflection model and how the fields are represented in the ground deflection model. So in this case, we are talking about two different fields, ELOS and EG, which are given by these expressions here, ELOS and EG, and we will use this expression to calculate the overall total field at which we get at the receiver side. Okay, before moving further, let us try to calculate the total field, for the time being ignoring the effect of the vectorial effect of the field. So the total field, which is actually sum of these two, we can calculate using the expressions here. This is ELOS and EG. So if you substitute in this expression and get the sum, so this E total field would be in scalar form would be E naught d naught upon d prime, which is actually this entire component is actually LOS field, LOS component. This is -1 is represented by gamma, and this entire thing is actually EG field, which is represented in the previous slide. Let me first talk about these magnitudes which are present here and here. Actually, the most important thing regarding this ground deflection model is that we are talking about different heights, this HT transmitter antenna height and receiver antenna height, and another distance which is represented here, distance d. In most practical cases, this d is actually much bigger than transmitter height. So let's say if your transmitter antenna height is let's say 50 meters and your distance is maybe 1 kilometer, so this 1 kilometer distance is much smaller, much larger than the transmitter height, and typically transmitter height is also greater than receiver height. So these distances, although it's not apparent from this figure because this figure is not drawn on a scale, but practically this distance is much larger. So this transmitter and receiver, they are at far away distance. And if you see, if we increase this separation, the difference between this wave and this wave, it gets smaller and smaller, and therefore the distances, this d prime distance here and d double prime distance of this way, they become closer and closer. So for most practical cases, since d is much large, so the difference between this d prime and d double prime is very small. Therefore the magnitudes of this LOS field and this EG field, this EG field magnitude here and LOS field magnitude here, they are virtually, they are same, and the magnitude wise they do not differ significantly. So we can approximate it, E naught d naught upon d is value, but that can be approximated as E naught d naught by d prime or E naught d naught by d double prime. So all these values are approximately same under the practical conditions, but this value d upon c and d by d double prime by c, this is actually representing the phase change. So phase change would be there, you cannot ignore the phase change, although the magnitude wise it does not make any difference, but phase wise there will be a difference between these two values. So we cannot approximate d prime here in the phase values here and here. So practically the both LOS and EG component, they have identical amplitudes, but the phase is different for both cases. So in that case, this total field which is available at the receiver side can be approximated by this relationship here that we have given here by equating these two. These two becomes equal. In that case you can take them out as common, E naught d naught upon d, and the rest of the part is mentioned here. So this can be approximated as the total value of the field. But here an important case is related to this phase change, how much phase change would be there. So next task is to estimate how much phase change we should expect when these two components of LOS and EG, they arrive at the receiver side. Before going towards phase change, let me try to calculate what is the actual difference we observe when we are at the receiver between these two distances, d double prime and d prime. So of course there will be a small difference, but still there will be a difference between d double prime and d prime. So let us represent the difference between d double prime and d prime as delta. So delta is the difference between distances. Actually we will be using this difference in order to in calculating the phase change, but for the time being we are ignoring the phase change and we are only focusing on the distance. Okay, how can we calculate the d double prime, the difference between d double prime and d prime? You can see a simple method which is known as the method of image is very useful in such cases. Actually, what is method of image? So let me go back to the original model here. So you can see this model here. So this is regular geometry. In method of image, we plot the mirror image of this geometry around this ground plane. So in ground plane you will see the mirror image that will facilitate us in calculating the overall difference in the distance. So let me try to plot the mirror image of the model. Here you can see this horizontal line represented here is actually the ground, and this entire geometry is replicated below the ground. So at ground you can see the mirror image here. The d prime distance is same, which is shown here, and d double prime, which is actually represented by this reflected path, this becomes equal to this direct length distance here. You can see this entire distance is actually d double prime. Further, if you see the transmitter antenna height, if I draw a horizontal line parallel to the height of the receiver antenna, you can see I'm plotting here. So you would see that this difference here on top, this is actually difference between the transmitter antenna height and receiver antenna height. So this can be written as ht minus hr. And if you compare the same thing with the line here, you can see here from this point. So this will be this entire distance. This is actually ht. This length is here ht, and this length here is hr. So this entire length from this point to this point, this can be written as ht plus hr. So this is the geometry by using the method of images. And if you look closer, you would see that from this diagram we can extract two right triangles, and those right triangles can be used to calculate distance by using simple Pythagoras theorem. If you are feeling difficulty in identifying those triangles, let me clarify those triangles in the next slide. So this is the same figure. I have superimposed two lines. One is one with the green color, and second with the yellow color. You can see this green part. This makes a right triangle here, where this height is actually ht plus hr. This horizontal part is the separation between transmitter and receiver d, and this line, this green line, is actually d double prime. You can see that by using Pythagoras theorem you can simply calculate d double prime. This d double prime would be given as under root of ht plus hr squared plus d squared, because the hypotenuse square is equal to under root of base square plus perpendicular square by Pythagoras theorem. Similarly, if you focus on the yellow triangle, this is again another right triangle. The perpendicular is given as ht plus hr here. Again the horizontal line is same, which is representing the separation between transmitter and receiver d, and this hypotenuse is actually this d prime. So this d prime would be calculated by Pythagoras theorem, and this can be given as under root of ht minus hr square plus d square. So from these two triangles we can easily calculate both the distances here, and we can calculate the difference by simply subtracting both the distances. Okay, we now have the difference of distance between these two values. However, this does not seems to be very good expression, but by simple analysis and by using some approximation we can get a relatively better approximation for this difference. So how can we proceed to approximate this distance? So let me do it by using by using the binomial theorem. You can see that here if we take this d square common in this bracket here and this d square common in this bracket here, so we can take this d square out, so this entire bracket would become independent of d. But when you are taking d, so this point you have to divide it by d here, and at this point you have to divide it by d here. So if you take d common here, you can see this d becomes out common as d is represented here as common, and in the bracket you would left up with 1 at one point, and the rest of the part would be divided by d square. Similarly with the other part, you would see this expression here. Secondly, you should see that this square root here and here, they can be written as the half power at both cases. So this entire expression, you would see that this entire expression is represented like this, and you can expect that this value is actually representing two binomial expansions. Like this part is one binomial expansion here, and second part, this one, is also representing another binomial expansion. You must remember that the binomial expansion of this sort, 1 plus x raised to power n, it requires that this modulus of x should be smaller than 1, but which is a valid condition here, because for most cases our distance is much greater than ht or hr. So dividing ht plus hr with d would give a value which is smaller than 1. Similarly, dividing ht minus hr with d would give a value which is smaller than 1. So these terms, this one and this one, these can be conveniently expanded by using binomial expansion, which is represented here, where these dots, they are representing the higher order terms. So this becomes delta d as common here is same 1 plus half ht plus hr square over d square, plus the higher order terms are indicated in dots here. Similarly, the second higher order terms are indicated by dots here. As we know that d is much greater than ht and hr, or in other words, this entire term is much smaller than 1. In that case, the square of this value will be even more smaller, and higher order terms would be significantly smaller, and those terms can be ignored. So if we ignore the higher order terms, so we would end up with this value 1 plus half ht plus hr square upon d square, minus this minus is because of this minus sign here, so minus 1 minus half this entire thing, and of course this minus 1 and plus 1 would go away, and in denominator there is 2d square in this term and 2d square in this term, and we can take this 2d square as common here as represented in next step. So this would be d into 1 upon 2d square, and we would end up with the these two whole squared terms, ht plus hr whole square minus ht minus hr whole squared. And these two terms can be expanded by using a plus b whole square and a plus b minus whole square formula, which are simple mathematical formula. If you expand these two terms by the appropriate formula, you would see that you would get the value of 4 hthr in this square bracket, and at the outer side this d would cancel one of the power of this d square, so you will end up with 1 upon 2d. So this is the result, and you can see that this 2 would cancel this 4 by 2, and you would see you can express this difference to be equal to 2 hthr upon d. So this is the approximation for the difference of distances which would occur between two paths which are indicated in our model. Okay, returning back to our original question, we were discussing about how to calculate the phase difference. So what is the phase difference when these two rays reach the receiver side? You know that if the wave travels one wavelength, in that case the overall phase difference that occurs is actually 2 pi. So one wavelength is equivalent to 2 pi. So the phase difference is actually related to distance because this is the normalization factor, that one wavelength is corresponding to 2 pi difference, and if any other distance is covered, like for this case the phase difference would occur because of the difference of distances d double prime and d prime. So you have to multiply by d double prime and d prime, which is represented by delta in our notation. So the phase difference that you expect between two rays at the receiver side would be 2 pi delta upon lambda, and we have already calculated the approximate value of lambda here, so we can estimate the phase difference theta delta by substituting the path difference value, which is 2ht hr upon d. So if you simplify, you would see that the phase difference at the receiver side will be 4 pi ht hr upon pi d. So you can see that this phase difference is actually dependent on d as well as the transmitter antenna heights and the wavelength of the wave which is being used. Sometimes we represent the phase difference in terms of radian frequency or omega. So how can we do that? If you go back to our previous case, this phase theta delta is actually 2 pi delta upon lambda. If you multiply numerator and denominator by frequencies, so this lambda into f becomes c, and this f into 2 pi becomes omega. So you can see it here. So I have multiplied numerator and denominator by fc, and this 2 pi fc would becomes omega c, which is the radian frequency, and c denominator would become c, which is speed of light. Okay, second important thing is the time delay, because two rays, they are following two different paths, so their arrival will be at different times at the receiver. So there will be a time difference between arrival of two components which are available at the receiver. So that time difference Td, it can be written as delta upon c. So this delta upon c, delta is distance and c. So you can simplify it to show it that this is equal to theta delta upon 2 pi fc. So this is the phase time difference between arrival of two different components. Okay, so our main objective was to calculate the total electric field ET. So as I said, before doing so we have to calculate the phase difference. So now how can we calculate the total field here? So returning back to the total electric field, so this is given by sum of these two fields. So we have two vector fields ELOS and EG which are arriving at the receiver. Magnitude wise, we have already discussed, we can approximate these two fields as E naught d upon d, but the phase at the receiver side would be different, and these two fields would have a phase difference of theta delta, which has already been calculated in previous slide. So how can we add these two fields, because we need to have a vector addition for these two. So a simple case is to plot them vectorially and dissolve them into their x and y components. So let us take x-axis in such a way that E field is along x-axis. So sorry, LOS field is along x-axis. So therefore the EG, the ground deflected field, will be at different angle, which is given by a specific angle of theta delta. So how can we represent it? So this is a simple illustration. So we have taken LOS field to be along horizontal axis here, and this EG field to be at a specific phase difference, which is theta delta. So LOS field, this can be the magnitude wise, sorry, I should have written magnitude here, I will correct it in the final slide. So ELOS X, actually it's not needed, magnitude is not needed because I'm talking about component, so ignore that. So the component does not require to be represented by magnitudes. So E naught d by d prime, it can be approximated by E naught d by d, as we have already discussed. And second, EG, it can have two components if you draw perpendicular here. So this horizontal component is actually cosine component, cos of theta delta, and this vertical component is sine of theta delta, which is here. So if we want to calculate the total field here, we can simply do that by adding the x components and y component, and the total magnitude is the square root of x component squared plus y component squared. So the total electric field would be given by ELOS x plus EGX, which are x components for these two fields, and plus this y component of EG, because there is no y component for LOS field. One important thing is that I have used a minus sign here, which is logical because this EG field is coming from ground deflection, and which has a ground deflection coefficient of -1. So this -1 is because of that ground deflection. So if you substitute these values which I have mentioned here in this expression of E total, you would see that E total can be written as E naught d naught upon d minus E naught d naught upon d, cos theta theta delta, and this one is the y component, which is E naught d naught upon d sin theta delta. And you can see that this E naught d naught upon d and this E naught d naught upon d and E naught d naught upon d, these factor is common in all terms, so we can take them common with the square, because it's square on top of every term. So E naught d upon d squared, and this will cancel out from square root, so this will be E naught d naught upon d. And in square root, this term would become 1, which is relevant to this term here. Second term would be, after taking out E naught d naught upon d as common, it will be cos theta delta, and third term will be sin theta only. And if you expand this term by a minus b whole squared, so it will be 1 minus 2 cos theta delta plus cos square theta. And you can see that cos square theta plus sin square theta, these are equal to 1. It's a standard trigonometric relationship that cos square theta and sin square theta, when they add up together, they will give 1. So this 1 plus 1 would give you a value of 2, and this 2 is here. So you can see that you have this value. If I take 2 as common here, so I have taken 2 common, so it will be 1 minus cos theta delta. Just to represent it in another form, I have multiplied it and divided by 2. So you can see that this entire factor, under root of 1 minus cos theta delta upon 2, this is trigonometric formula of sine half angle, sine theta delta by 2. So this will become a sine theta by 2. This 2 into 2 becomes 4, and after square root it will be 2 here. So the total electric field is given by this expression, E total of 2 E naught d upon d sine theta delta upon 2. So this brings us to the approximate value of the total electric field at the receiver side. However, we are interested in calculating the total power, so that we will discuss the power in our next lecture. But for the time being, assuming this expression, let me try to show the curve of the received power. So it will look somewhat like this because of this sine theta delta factor. You would see that there are variations in this curve here. Actually, why these variations are occurring? Because you can see this sine theta delta would be changing. Actually, these two fields which you see in the original model here, these fields would be these fields would be arriving with a phase difference. So whenever there is a phase difference of 180 degree, so you would expect a destructive interference, and whenever phase difference would be 0 degree, you would expect a constructive interference in these two waves. So basically these two components of wave, they are arriving at the receiver and they add up destructively and constructively at different distances. So these deep values, the fades or these small amplitudes, they are relevant to those destructive interferences. But and these high values, they are related to those parts where you have constructive interference. However, this phenomena is observable at only smaller distances. It's only for small values of distances you would see this thing. But for typical cases, we have D, which is much larger than HT, HR, or even some of these two values. In that case, we can further approximate the previous expression which we have discussed here. But we will discuss the further approximation in our next lecture, inshallah. So having larger distance means the phase difference would be much smaller, and we would be able to make some approximations to calculate the received power. So this lecture we would stop here, and we will continue our discussion related to this ground deflection model, and in our next lecture we will discuss how can we further approximate this expression for larger distances, and how can we relate this E field with the received power. Okay, thank you all.